So the time domain is what we think about and we perceive in our everyday life. So in our world, time marches forward and we think about things happening over time. And so the time domain is very comfortable and familiar to us and typically is represented by a plot versus time. Not much to say in here, but if we think about the other domains we work with, namely the frequency domain, this is a little bit different. The frequency domain is an abstract concept that we've generated that really helps us deal with signals in a more robust way. And these are representing the signals by the frequency components that make them up. If you remember from the Fourier series that you can take any time waveform and break it up into a series of cosines and sines, and the frequency domain just simply plots the magnitude and phase of those cosines and sines that when you add up create the time domain signal that you are interested in. And we generally represent this in F, or we can also talk about omega. Typically as engineers we talk about F because all of our instrumentation is in frequency directly. Omega is used quite often because oftentimes analytical calculations end up in radians and omega is more useful. So we can go back and forth between the two almost interchangeably. The only thing you need to make sure of is that if you're doing a calculation, it may likely be in terms of omega, and if you want to convert to F, you need to use the formula right here. All right, so the question comes in, if we have time domain is what we see in real life, if you will, and frequency domain is this concept, how do we measure these two? And so you should know that there's two primary instruments that we're going to use to measure time and frequency domain. So let's start with the time domain. And this is a picture of an old oscilloscope, but you probably already know that we use the oscilloscope here to represent the time domain, and so the time axis is actually right here. And then of course if we want to do the frequency domain, we use a spectrum analyzer where this axis right here is in terms of F, and these are simply plots of the magnitude of each frequency. And we're going to learn to use both of these. It's expected that you probably already know how to use an oscilloscope, and we're going to go over some of the basic functionality of a spectrum analyzer and also go into some of its advanced features, because one of the things about radio systems is that we deal with signals of very low magnitude and are very low power, so microwatts, maybe even picowatts, and it turns out that we have to use some of these advanced features in order to be able to see these really small signals. So we'll talk about that more as time comes along. All right, now we've been talking about the time versus frequency domain, and as you know, we can go between those two using the Fourier transform. And so the Fourier transform will take us from a time domain signal into a frequency domain signal, as you know. And just as a reminder, if you change a signal in one domain, it gets changed in the other domain. However, the change is not the same. If we change this signal here, x of omega does change, but the change happens through the Fourier transform. So except for linear multiplications by scalars, changing x of t, for instance, shifting in time, does not just simply shift that on the axis, but this should be review for you. And so here is a couple examples of Fourier transforms, and one of the things we want to show you here is sort of how things look in the time domain and how things look in the frequency domain. So if you remember, the Fourier transform of a square ends up with a sinc function here, and you're probably familiar with that. If we were though to take a low pass filter, and I'll draw that in the frequency domain, so imagine I put in a filter that has a pass band like this. So it's pretty easy and intuitive from the frequency domain to realize we're just going to basically filter out all these sides, and this is the signal we get. But you need to remember that in the time domain it has an equivalent one, and it smooths it out. And we could have actually thought about this directly in that a low pass filter is going to remove all the sharp edges and smooth things out. So here's a great example of how operating in the frequency domain here is very easy and quick, but there is an equivalent time domain change that we just need to keep in mind.